Logarithms. Now, I plan on only saying this once. One, the things that are in the beige boxes in this assignment, what you can do is you can grab, do the copy, paste, screenshot it. And I want you to go and make yourself just a sheet of paper that has these things on it. The reason why is memorization is a good thing. Understanding that is great. But I don't want you to get mixed up which ones go where. I want you to be able to use this. I'm not worried about the memorization part. So, this beige box here, this is the key to dealing with this thing. Okay? Y is equal to, or X is equal to BY and this function. They go back and forth. This is the information that you need to have to take one from the other and the other to one. Okay? So, okay, this is okay, but you don't need to have this put in there. This is something that you should be able to recognize what the graph looks like with it. Okay. Natural logarithms. I want you to make sure that you have that in there as well. These basic properties of logarithms. Again, screenshot it, copy it, put it into a word processing document to have. And these. I want you to have ready access to these so that you're able to go and get these without a problem. Okay? Does that make sense to you? So I don't think there was anything else that I wanted in here. The Richter scale stuff, not necessarily. So let's get back to dealing with this. So I want to write these in terms of a logarithmic function. So if I am supposed to convert these, now this idea that we have from right here, now this is written in the form x is equal to b to the y. So that means our x is going to be here. Oops, so let's check wrong one. X is over here, b is here, y is up here. So when I write this, it's going to be 2 is equal to log base b, which is going to be 9, of 3. Now logarithms go back to, there's a dude up there called John Napier, called Napier's Bones. He actually had these all set up. It works out very well for finding an unknown exponent. There used to be books, actually you can still find them obviously, but there were books that just had tables and tables of logarithmic calculations in them. It simplified things greatly. Okay. So now, just kind of continuing on with this a little bit. So here, I got 4 to the negative 1 is equal to the 1/4. So what that means is that I am going to have log base b, in this case it's going to be 4, of 1/4 is going to be equal to negative 1. Next one here, c. That's going to be log base 5 of 5 is equal to 1. So the last one there, that would end up being log base 3 of x is equal to y. That's all it is. Just another way of writing this stuff out. Now, we use logarithms to simplify calculations, and they actually do simplify them very much. But this is the key for going back and forth between them. So let's take a look-see at this. So now I want to go back the other way. That did not work the way I wanted it to. So now I've got the logarithm and I want to go back to it. So I've got log. This is the b, this is x, and that is y. So that means 2 to the 4th power is equal to 16. That means 10 to the negative 4th power is equal to 0.0001. That means 6 to the 0 power is equal to 1. And by the way, that last one there, log base whatever you want of 1 will always be equal to 0. Why? Because anything to the 0 power is 1. So really all that we're doing here is right now is just looking at how we can get back and forth between the two systems. So, got to start having some fun with this stuff, right? We're going to take a look at evaluating this now. So, first thing it wants us to do is write that in exponential form. So, that's fairly simple. That's just going to end up being 2 to the y is equal to x. So now, use the exponential form from part A to find y when x is equal to 8. So I want to evaluate this. So that means 2 to some power of y is equal to 8. Well, how many 2's multiply together to equal 8? Well, 2 times 2 is 4 times 2 is 8. So that means 2 cubed is equal to 8. So y is equal to 3. We want to go and rewrite this back into a form with exponents so that we can see what it's going to be equal to. So for this one here, that means 4 to some power y is equal to 1 over 16. Sometimes it's not all that easy to see. So what we can do is rewrite this value as 4 to some power. Well, I know that this is going to be 1 over 4 squared. And I know I can bring this up, and it's going to be 4 to the negative 2. Okay. So now, what's y equal to? Y is going to be equal to negative 2. Easy enough. But you have to have that understanding of rewriting something in terms of a base to a power. Look at this one here. This is going to be 10 to some power y is equal to 0.001. Now, this is where understanding fractions makes a whole ton more sense. Okay. So this is going to be equal to 1 over 10 hundreds, thousands. 1 over 1,000. Can I rewrite 1,000 as 10 to some power? Well, wouldn't that be 1 over 10 cubed? And wouldn't that be the same as 10 to the negative 3? So what is y equal to? Y is equal to negative 3. That's it. No more, no less. But if you can go through that process and get the base to a power, you're getting closer. Okay. Graphing a logarithmic function, that's not that big of a deal. But I want you to understand something. Your calculator can't do it. Your calculator is set to work with base 2, not base 2, base 10, and the natural logarithm base e. You cannot go and put this into the calculator and have it go through and do this. It doesn't work that way. Okay. So, how in the world do I do this? Simple enough. I need to graph that out using x and y. What could I do? Can I rewrite it? So x is equal to 2y. So I put in a value here for x. Would that make sense to do? And work backwards. So I'm going to go through that here with you. Now the original problem that we had here was y is equal to log base 2 of x. I cannot, look at that and say, oh, I know exactly what I put in for x, what it's going to be. If I have 2 to the y is equal to x, that should be y up there, I can sit here and think about things a little bit easier. So my question would be, what happens if x, say, I want to start off with 1. We'll start off with the easy numbers. I want x to be 1. What does y have to be in order for this relationship to work? Well, it would have to be 0, because 2 to the 0 power is going to be equal to 1. So I've got my coordinate. Okay. What happens if I want it to be equal to 2? In other words, 2 to what power is going to be equal to 2? Well, that would end up being 1, right? So we've got that coordinate. What happens if I want 2 to some power to be equal to 4? I want 4 now. What is that going to be? Well, that would have to be 2 squared. So I get squared here. What happens if I want 2 to be equal to 8? Well, that's 2 cubed. So we get that. Would I want to even begin to consider getting 2 equal to 10? Would I want to think about that? Would I? Oh, God, no. Because 2 to some power does not equal 10. I don't even want to begin to think about how to get there. So when we're looking at this, we want to be thinking of the multiples of whatever the base is. If the base is 2, I want multiples of that. Now, that also means that I am going to go backwards on this, and I'm going to do the reciprocals. Okay? If I look for a 2 here, I'm going to look for a 1 over 2. So 2 to what power is 1 over 2? Well, that would be 2 to the negative 1, yes? So that means that for x being a half, negative 1 has got to be y. It's a little bit different to think about it in these terms than what you've had to do before. Before, you've plugged in a value for x and got something out. Now you have to kind of think of it backwards. If I want this, what do I have to plug in for y in order to graph out this logarithmic equation? Likewise, if x is to be 1/4, well, 2 to what power is going to be equal to 4? Now this is where I'd rewrite it and say, well, 4 is the same as 2 squared. Now I know that it would have to be 2 to the negative 2, right? So that's why we have y here is at -2. So I can plot those points and I can graph them out. This is going to take a little bit of time to rattle around in your mind and work with it. This is one of these opportunities here now that just because I assign specific problems for it doesn't mean I want you just to do that. If you're having difficulty, do more problems that are in there. Work them out. Try and figure it out. So, the nice thing is there are some basic ideas that it's going to look like. A logarithmic function is always going to look like this. It's always going to go through here at 1. Okay. Unless it's got the, changes that are going to it, moving it up, the translations. The base or the parent function for this is always going to look like this. This is going to be if you have a base that is between 0 and 1. Then you're going to see this. If it's greater than 1, it's going to look like that. When we have these logarithmic properties, we want to use these to simplify things off. So I want to simplify these. What are they going to be? Now I look at this first one here, and I kind of want to go back to my properties. So I take a look at this and I want to know which one does A resemble. Well, log 5, 5, 10. I want to look for something where these two are the same. Well, if I look at number 1, it's got BB. Okay, so that looks promising, but I got another number up there. So I got BB to the X. That means it's going to be equal to X. So I look at this. Oh, that's easy. That's 10. Why? Because it fits this particular pattern. What's B going to be? That's 1. Why? Because it fits this pattern. Log base B of B is equal to 1. Why is it equal to 1? Well, if I had log base 4 of 4 equal to X, that means 4 to the X is equal to 4. What does X have to be in order for it to work? 1. So now, log base 4 of 1, what is that going to be? Well, I had said before, whenever we take a log of 1, it's always going to be equal to 0. Now, what about D? There's no number down there, is there? Well, this is where knowing what bases we have available comes into play. Your calculator is set up in base 10 logarithms. Okay, so when you see that little word or that little button down there that says log, this is base 10. Okay. So when I look at this, I see log of base 10 to the 7th power. So I could put 10 here to the 7th, close it, hit enter, and I'm going to get 7. Why? because this would be written as log base 10 of 10 to the 7th power, which we seen over here was just the exponent. So the calculator can deal with anything that is in base 10 power. Also, if you do not see a base on log, that means it is going to be base 10. Now, next one, ln e cubed. This is equal to 3. You'll notice that there's also an ln key on your calculator. If I go and hit ln, I hit second. Above that is e to the x, and I put in 3, close these, and I'm going to end up with 3. Why? Because the natural log appears so often, it was given its own notation. This is essentially the same. ln is the same as log base e. And now you'll see that, well, if I'm taking e to the 3rd power, these are the same again, so it must be equal to 3. Now are you beginning to understand why I said that I wanted you to take these properties, have them printed out, and have them available for you? I don't want you to try and memorize them. Memorization will actually come through use. You'll become more familiar with what things are. So now, last one. When I look at that, again, I see nothing there for the base, so that tells me that the base must be 10. So I know that I'm going to have log base 10. But now, if I could get that is 10 to some power, that'd be great, right? But if I got 1 over 10 to the 3rd power, that means it's 10 to the what power? Negative 3. So this one here is going to be equal to negative 3. That's it. But this is understanding and utilizing those properties. Or as I always like to call it, mental gymnastics. Okay. Let's try this. Grab some more of these wonderful little things. Here, there, paste. That, this, that, there. Okay. We want to rewrite each of the following expressions as a sum, a difference, product, logarithms. One of the reasons why where logarithms exist is so that they were able to do complex calculations. If you like, they're the scientific calculator of the day. Okay. So let's take a look at the first one. I have log base 4 of 5, then I have in parentheses x minus 7. Which one of these is it going to fit? Well, you'll notice that none of these have addition going on in them whatsoever. They only have multiplications. So for A, that would be log base 4 of 5 plus log base 4 of x minus 7. Can't do anything else with that x minus 7. This is what it's going to be. Okay. Now, it's kind of like what you've noticed, hopefully, over time. Addition and multiplication tend to go together. Division and subtraction tend to go together. If I am looking at B there, I've got natural logs. Natural logs behave in exactly the same way. So that means this is going to be ln of e squared plus ln of e plus 3. However, I can go through and still do another simplification. E squared. If you look down here to the power property, this would be written as 2 ln of e plus ln of e plus 3. Now, why in God's name would this be easier to deal with, right? If I had this calculation to do back in the day, I would have pulled out a book that had the natural logs of E, or natural logs, calculated out. I'd look up what number I was wanting. It would give me a number, so I know that I'd multiply it by 2 and add whatever that was going to be to it, which is by far easier than the original calculation would have been. C, division. Well, that means that I am going to simply have log of x minus 8 minus log x. All done. That's it. That was quotient property, so I used it there. I take a look at D. What's all going on with that? Well, I see a log 4y6. Power property. Power property gives me log base 4 of y. Well, what would be out in front of it? 6. There we go. What about the last one, E there? Now, this one could be dealt with in a couple of different ways. You could apply the division to it, or the quotient property if you wanted to, but that would be the ln of 1 minus the ln of 5. And I'm going to go through that here a little bit and show you what happens. This one's a little bit on the more fun side. So, one way I could look at this would be ln of 1 minus the ln of x to the 5th power. But what did we say that the logarithm of 1, or natural logarithm of 1, was going to be? Well, if I go back to that property, that's equal to 0, right? So that means this would be 0 minus ln x to the 5th power, or just minus ln x to the 5th. Now, I said that there was another way that you could have thought about this. Could have I gone and done this to it and said that this is the ln of x to the negative 5? If I do that, then that would be the same as negative 5, ln x. By the way, I've got an exponent out here, don't I? Could I put that exponent out front? So that would be minus 5 ln x. Got it to the same place. Again, this is why looking at it and seeing what is available isn't always going to be obvious to the same two people. One person will look at it and see something, another person looks at it. Write it out, show the work, that way you can justify it to each other when you're looking at this. All right, so what else do we got to play with here? That's going backwards. So, here endeth the lesson. I want you to start working on this, and we can go over questions from there.